Hi there. Today we're going to talk about some more special purpose op amps. We're going to start out with the operational transconductance amplifier. Sounds pretty fancy. It's a mouthful, operational transconductance amplifier, but it's basically a variable gain or voltage controlled gain amplifier. That's the way I like to think about it. So it has, this particular amplifier has a separate input which is called V mod, and that's, the mod stands for modulation. And a lot of times these are used as amplitude modulators. So what this is here on the output of this amplifier is a current source. That's what those two circles are. And the mod input goes into that current source and adjusts the current based on this voltage. So that's where the transconductance comes from. It's a current out versus voltage in. And whatever input comes on the, whether voltage is applied to the input here at V in, that is modulated in amplitude by this V mod voltage. So in this case, we're going plus 10 volts to minus 1 volt at kilohertz. We're modulating that in amplifier, in amplitude, amplifying this, or modulating this 1 megahertz waveform with this sine wave here, this 1 kilohertz sine wave. And this is what you end up looking like here, this V out. So you get this kind of like this envelope. So the higher the amplification, the greater the output is, and then when V mod comes down, it's less amplification. So again, this is used a lot in amplitude modulators. It's also used in voltage controlled filters. If you can imagine connecting this output to a filter. We do filters at the end of this course, but a filter which produces a greater voltage at higher frequencies. Okay, what's going to do is going to cause this amplifier to boost those high frequencies as well. And if you do the inversion of that, it's going to be a low pass filter. In other words, a filter that attenuates high frequencies. Lots of different uses for this OTA. There is some specific parts. I think we get into that, but here's the curve. Oh, that's a log amp. I don't want to look at that yet. Oh no, I think we do. Yeah. Okay. Yeah, there are some specific parts for an OTA, which you can look up in DigiKey. Just type in operational transconductance amplifier, and you'll see some specific parts that are used for that. The next kind of amplifier is a logarithmic amplifier. Again, this is another good example of the operational part of operational amplifiers, performing a mathematical operation. A lot of times we need to be able to do what's called compression, dynamic range compression and expansion in signals. If a sensor, for example, outputs a very low voltage, a very low level signal with a low input, in other words, a pressure transducer, let's say, or temperature transducer, and at very low pressures, it outputs a very low signal, but at very high pressure, it outputs a huge signal. Well, you want to be able to delineate some of the lower pressure values, let's say, lower pressure deviations, and to do that, there's not a whole lot of granularity. So what we'll do is we'll put it through a log amp, and a log amp will amplify low-level signals and attenuate high-level signals. So it's a non-linear amplification. So anytime you want to do that sort of a dynamic range expansion or compression, we call it, you use a log amp. This is very common in audio circuits for microphone circuits to prevent oversaturating the amplifier, the microphone preamp. So somebody's talking very softly, it'll amplify that, but if they start shouting into the microphone, it'll reduce the gain. So it keeps everything in the sound from getting crunchy. There's companies that have based their entire business on making dynamic range compression circuits and boxes for this sort of reason. And a lot of recordings, musical recordings and so on use all of them do in some way. Some of them use it too much, and you can tell when it's just there's no character to the sound anymore, and it becomes very, very unexciting. So it can be overused sometimes, but by and large, for all sensor circuits and certainly microphone circuits, there's some sort of compression circuit that is very commonly used. So here's the curves. Here's a log curve right here. Okay, so you see it's nonlinear. So as and this is showing the actual current voltage curve of a diode. All right, so this is the real current voltage curve for a diode. So as the current for the diode increases, the forward voltage increases, but not as much as the current, right, in a relative sense. So down here we got this logarithmic characteristic. This one over here is a linear curve. So you see the difference between the two. So if we put a diode in the feedback path of an op-amp, regular op-amp, you're going to impose on the gain of this op-amp that nonlinear characteristic. So this takes the place of the feedback resistor. And the feedback resistor is all of a sudden a nonlinear resistor. It's got a logarithmic characteristic to it. So voila, you have your log amp, okay? So again, it amplifies small currents more than larger, which causes data compression or signal compression, okay? Photodiodes it's commonly used for photodiodes, which is a sensor, a light sensor, okay? And it says here, current from photodiodes can range, excuse me, over 5 decades. Okay, so that's 5, right? It's 5 tens, so it's 10, 100, 1,000, 10,000, 100,000. So all the way from 10 to 100,000. That's a really big range. So when you're operating down in the tens and hundreds, you're not going to get a whole lot of variation. But as soon as you get past 10,000, then you do get a lot. So you really have to do something to pull out that small stuff, if you will, the small signals. And the log amp is what we use for that. Now, if you just put a regular amplifier in there, think about that. Oh, why don't I just multiply everything by 1,000? Okay, that'll work great for when the signal's really low, like down in the tens or hundreds. But as soon as the signal starts getting higher, up into 1,000 and 10,000, you're going to saturate your amplifier. You haven't got that much dynamic range, so you have to compress that dynamic range, and that's what a log amplifier does. Now, how do you put it back? Well, we'll look at that in a minute here. This is the equation. You're going to want to put this on your equation sheet. Okay, V out is the minus 25 millivolts times the natural log of Vn divided by IR, R1. What's IR? IR is constant. That's the reverse leakage current for a diode. You can pull that out of the data sheet. That's constant. R1 is constant. So the only thing changing here is Vn. So you get a V out versus Vn. Very nice equation. This is a button. This ln, this natural log, is a button on your calculator. So you're going to want to write this on your equation sheet for the next midterm and the final, so that you know how to use it. And obviously there's homeworks and examples and text. You're going to want to do all of those. I think this is an example here. V out, assuming that the reverse leakage is 50 nanoamps. We have 11 volt input. So you crank that equation out and you get minus 307 millivolts. Now, notice something else. This is an inverting circuit. So it not only compresses, but it inverts. So if you need to flip it around, you have to put it, in other words, make it non-inverting. You have to put another stage on here, an inverting buffer. And you should know how to do that from the very first chapter. An inverting buffer to take that minus 307 millivolts and turn it into plus 307 millivolts if you need to. You may not need to, depending on the application. Certainly for AC signals like audio and things like that, you don't need to do that because it's an AC signal unless you have to worry about phase, which usually for running, just do it like a microphone input, you don't have to worry about that. You can replace that diode with a BJT, and I think this is what we do in the lab, okay? And it gets rid of some it gets rid of some offset problems and some bias current errors. So BJT is usually used better. It's a very similar formula. IEBO is again right out of the data sheet. It replaces IR, so this is pulled right out of the data sheet for the particular transistor. For your homeworks, examples, and for any test question, you'll be given IEBO or IR, either one of those, so you can solve the problem. And again, they are available in IC form, as I was trying to say earlier, the Max 4206 from the Maxim company. I think they're owned by TI now, or Analog Devices or something. But lots of log amps. You can again go on DigiKey, type in logarithmic amplifier, and you'll come up with a bunch of them. There's other techniques that are used nowadays. Not only this, not only the BJT or diode and feedback, but there's other techniques that are used, and you could probably guess that they're more digital in nature. Sometimes they'll take the input and the analog input, digitize it, put it into a table, a logarithmic lookup table, and then output it again to a digital to analog conversion. So all in one package, you got this little state machine, if you will, a little lookup table, and those can be a little more linear, a little more true. And I encourage you to go on DigiKey and look up logarithmic amplifier and try to see what the different kinds there are. We focus on this particular type in this class, but it's important for you to know that there's other ways of doing this and other ways that are in some cases more common. This is pretty good though. It's 4206. Goes over 5 decades, measured from 10 nanoamps to a milliamp. So you think about that, 10 nanoamps. That's not very much current, and you're able to actually discern that variation way down in there. So how do you put it back from log? You have to put it back to make it linear again. The way you do that was obviously with anti-log, right? Log and then anti-log. So antilog is kind of like another key on your keyboard, okay? And this is the formula for that. You want to put this on your formula sheet. So minus RF, that's the feedback resistor. They move the transistor, the logarithmic element, if you will, to the front here, to the input resistor spot. And it's IEBO, the same parameter for your transistor, anti-log Vn divided by 25 millivolts. Very similar equation. You're going to want to put this on your equation sheet too. So here's an example of Daytel LA8048 and 8049 are companion parts. One's a log, one's an anti-log. And again, there's other ones out there that do it similar to what I just described, using a lookup table and things like that. But they're all viable parts. Okay, we're going to look at that. So that was log and anti-log amps. So look at some other op-amp circuits. Now, these are really cool. I like this this chapter specifically because there's all these really clever circuits. So this one's a constant current source, this particular circuit. So if you look at this, we have a voltage source here feeding into the input resistor. Now, there's a 0 volts shown here. Why is that? Because that's what? Virtual ground, right? That's this, because these two, you have this feedback, so these two terminals on the input are at the same potential. If the non-inverting is at 0 volts, well then the inverting is at 0 volts also by virtue of virtual ground. So that results in a constant current going through Ri, constant current going through Ri. Where does that current go? Doesn't go into the op-amp. We say the op-amp doesn't need any current. So it goes all the way over through the feedback and through the load resistor. Now this load resistor, if it changes, as shown here, it's a potentiometer. If it changes, that value changes. Is the current through it going to change? No, it is not, because there's a constant current here. This stays constant. So that's pretty cool. You can have a constant current going through a load. So if this load gets heavier, in other words, a lower resistance, the same current's going to go through it as if it's a light load, a higher resistance. Now there's limitations, obviously, because your OpAmp power supply will run out of rail if you go too high or too low. But this is a very common circuit for power supply circuits, for example, and LED circuits. LEDs like constant current, right? They operate off of current. They have a voltage drop, a specific voltage drop, but they like to operate at a constant current. So your LED lighting and things like that normally have a constant current source circuit in them. Current to voltage converter. Okay, so you have a current coming in here into the input. That's 0 volts. That current goes through the feedback resistor and produces a voltage across RF. Well, this side of RF is at 0 volts, again, because of the virtual ground. So that current, all of it goes through RF and produces a voltage in accordance to Ohm's law, the IR drop. So whatever V out, whatever current is going through that resistor, RF, is going to produce V out. So that is a constant, not a constant, but it's a current to voltage converter. Now, you might ask, why can't we just use a resistor and run a current through a resistor? That's going to produce a voltage output, right? Well, yes. But the problem is if you put a load on that circuit, on that resistor, it's going to change the whole thing. So unless you buffer that, it's going to change the entire circuit. And it's not going to be a current to voltage like you think it's going to be. Like that, whatever resistor you choose, is that resistor going to ground, that's going to change by the load, because that's another resistor going to ground. The load is. Whereas this circuit, that's not the case. If you put a load out here, whatever voltage is produced here is not going to change. It's only based on RF, not your load resistor. Very common circuit for that sort of application. Voltage to current converter. This is just a regular OpAmp circuit, regular non-inverting OpAmp circuit. Should recognize that. It's from our chapter 12, I believe. And here we know that this voltage here at the inverting terminal, again, because of how op-amps work, right? The two inputs are the same voltage with negative feedback. So this is going to equal Vn, this point right here at the inverting terminal. That Vn is across R1. So whatever voltage appears here, appears right here, and produces a current in R1. So it's a voltage to current converter, because that current is directly related to Vn. Okay, so that goes through R1. And lastly, a peak detector. Okay, so this one we have a diode that obviously passes current only in one direction. So as Vn rises, the output voltage of the op-amp rises and charges this capacitor. Now, if the voltage gets to a certain voltage, let's say 5 volts, okay, and then this Vn starts dropping below 5 volts, what happens? Well, this output is below 5 volts. This is 5 volts here at the capacitor, but the output drops. So the diode is back biased, so there's no current flow. So therefore the capacitor holds that peak of 5 volts. until you short the capacitor out or the capacitor charge dies out. So, but if the input goes above 5 volts, again, the diode now becomes forward biased and it charges the capacitor more, again, holding that peak. So typically these circuits have a little FET device here to short out the capacitor momentarily. So perhaps some of you are familiar with like LED VU meters that bounce up and down, and they'll pick the peak and then go down, pick the peak of the audio signal. That's what this circuit is. That's what this circuit can be used for that. Okay? So I think that's it for today. Next week is chapter 15. And let me know if you have any questions about these special op-amp circuits. That's the end of chapter 14. Okay? We'll talk to you all later. Bye.